All right, let f be a non-negative measurable function on a measurable set E. We want to prove that the Lebesgue integral over set E of f with respect to the measure equals 0 if and only if f equals 0 almost everywhere on E. All right, so first let us define what this almost everywhere exactly means. Well, almost everywhere basically just means that if we have a set A equals x such that f equals 0, or f is not equal to 0, x is not equal to 0, aka this doesn't hold, measure of A is equal to 0. So aka where the condition does not hold, that measure, the measure of that set of x is equal to 0. So that's what almost everywhere means. Okay, so let's first prove the reverse direction. This direction is going to be pretty simple, pretty straightforward. So proving this direction. Okay, so suppose f equals 0 almost everywhere on E. Then the measure of E set minus A over, letting A equal the set of x such that f of x is not equal to 0. We have E, or f equals 0 on E set minus A. All right, and since f is equal to 0 on this set, we know that E minus A of f d lambda is equal to 0. But also see that the Lebesgue integral with respect to A of f d lambda is also 0. And why is that? Well, if we think about the definition, this is just going to be the supremum of our simple function, all the simple functions that take on the values of c such that the simple function is non-negative and also less than or equal to f. Or actually, let's make these ai since we're doing it over this a, where all these, the union of all these ai's, we have constructed this to be equal to a. And so we see that since A is a subset of E, this is just measure of AI. And since the measure of AI is less than or equal to the measure of A is equal to 0 and measure is non-negative, we know that each of these AI's are equal to 0. So the Lebesgue measure of f with respect to A, 0. Or I guess over this A is 0. Okay, so now we can use this property where if we sum two integrals over different sets, their sets we combine the sets. So this is equal to 0 because both of these are equal to 0. Okay, so now let us prove the forward direction. And this direction's going to be a little trickier. So we're gonna have to cleverly construct a set for this direction. So now we suppose the Lebesgue integral of f over set A, E is equal to 0. And now we're gonna suppose we have a sequence of sets a sub n equals, this is just going to be the set of all f sub f of x greater than 1 over n, where we have n equals 1, 2, 3, ... Of course, all these x are also in E. Okay, so now we see that when we take this, since a sub n is a subset of E, we have that this is less than or equal to, so the integral over each a sub n is less than or equal to the integral over all of E. And of course, since all of these a sub n's are the values at which f of x is greater than 1 over n, we can bound this below by 1 over n d. All right, and furthermore, by the definition of, since this will basically just be like a constant, we know that that's just going to be equal to 1 over n times the measure of a sub n. So now see that we have bounded the Lebesgue integral below, and now we're thinking, well, how can we relate this to f? How can we show that f is equal to 0 almost everywhere? Well, we also want kind of like an inequality, and if we know that the measure of something is less than or equal to 0, we know it must be equal to 0 because measure is always positive. This makes us think of countable subadditivity. So since we have 0 is greater than or equal to 1 over n lambda an, we want to somehow turn this into this statement about f being 0 almost everywhere on E, and remember that just means the measure of the set A is equal to 0, where A is the set of all x such that f of x is not equal to 0. So the condition, aka the condition, is not true. Okay, so we see these a sub n, we see that the union of all of them is actually going to be A. And why is that? Well, you can see that as, so the countable union, you can see that as n approaches infinity, this will approach 0. And that's just where f is non-negative, and f is already non-negative, so it's going to be f, which is basically just going to be approaching the places where, all the places where f is not 0, aka non-negative. Okay, so now that we have that, we know that by countable subadditivity, the measure of A is equal to the measure of equals 1. And this is going to be, kind of just think of it as in terms of like triangle inequality. Sum of n equals 1 of measure n. All right, and we see that this is positive, so that means that this must be equal to 0 by our logic. So we know that each of these is 0, so that's just going to be equal to 0. And again, the measure of A is less than or equal to 0, greater than or equal to 0, since measure is always non-negative. And then that means that the measure of A is equal to 0, aka the set at which f of x is not equal to 0 has measure 0, which means f equals 0 almost everywhere on E. And we're done.